Everyone, welcome to the 25th lecture in the series. This lecture is actually a continuation of the previous lecture which we were learning about binary search trees. With the previous lecture, we covered some of the operations permissible on a binary search tree, namely search operation, how to find the minimal and the maximal element on a binary search tree, and how to find a predecessor and successor of a node in a binary search tree. In this lecture, we are going to study about two other operations that are permissible on a binary search tree, namely insertion and deletion. So, let us see each one of them in detail. So, first is we are going to see how to do insertion in a binary search tree. So, here insertion can always happen, but at the leaf level. So, that is one of the things that is true for a binary search tree. And when we want to add new elements onto an existing binary search tree, we will follow the condition for search tree property. So, we just check the new node's key value and we compare that to the root, and if it is less, we try to position the new node along the left subtree. If it is greater, we try to position the new node along the right subtree. So, first of all, whenever we want to insert a new node into a binary search tree, we need to follow the procedures we adopt for creating a new node. We have to allocate space for the new node, obtain values for the new node, and then after obtaining the data value for the new node, we compare it to the root and then decide whether it should be inserted along the left subtree or along the right subtree. So, for that we check whether key of x is less than v. If so, we move to the left subtree, and if it is greater, we move along the right subtree. So, here beginning at the root, we have to go down the tree. As I said, whenever we do insertion, we do insert the new node at the leaf level, right. So, we have to go down the tree, but as we move along the tree, we actually maintain two pointers, one is x and y. So, here pointer x traces the downward path, and we make use of it to point to the current node, and pointer y is a trailing pointer, which means it just points to the node that is before x. So, we call that as a trailing pointer. So, at every point of time, y will be following the path of x. So, we call that as a trailing pointer. Let us consider an example of inserting a value of 13 onto this tree. So, let us imagine that we have created a new node and the new node's key value is 13. So, we immediately compare the key with root, which is v here. So, v is 12 and key is 13, key of x is 13, and so as 13 is greater than 12, we move along the right subtree. We compare 18 and 13 is less, so we move along the left subtree of 18. We compare 15 and 13, as such 13 is less. So, this is the place where 13 has to be added, and 13 would naturally become the left child of 15. So, this is how we do insertion in a binary search tree. You have to know two things, that first of all, for facilitating insertion, you are supposed to create a node, and always you need to remember that when we add a new node to a binary search tree, that to insertion in a binary search tree, always the new element will get added up at the bottommost level or the leaf node level. So, here I have given you one more example to better understand how insertion happens in a binary search tree. So, as you know, we are going to add a new element named 95 into this existing tree. We have a tree, of course, the tree looks slightly balanced, and the root node of the tree is 50. So, we compare 95 and 50. In our case, 95 is greater. So, we move to its right subtree. So, the root at the right subtree is 75. Now, we compare the key value, which is 95 with 75. As such, this value is greater than 75. So, we move along the right subtree. So, now 85 becomes the root of this right subtree, and we compare 85 and 95. As such, 95 is greater, and so this is where your 95 should get added up. Just because it is greater, we add 95 as a right child of 85. So, this is how we perform insertion on a binary search tree. So, now we are going to learn an algorithm for doing insertion in a binary search tree. So, that is the reason to familiarize with the terms used in that algorithm, I have added up this example. We are going to insert an element 13, and as such our root is 12, and so here insertion operation always begins with root element in a binary search tree. So, we fetch up the root in the variable x. So, we fetch the root of the tree and put it up in x, and for y we initialize with the value of null. So, by this time you remember that whenever we do insertion, we are going to take two pointers, one for pointing to the current node, which is x, and other one should be a trailing pointer. So, for starting this insertion operation, we first initialize x with the value of root and y is initialized to null. Now, we have to make a comparison of 13 and 12. 13 is greater than 12. So, we move along the right direction or the right subtree, and so we position x along 18 and y takes the place of x. So, y is a trailing pointer. So, it stores the value, or it points to the value that was pointed to by x earlier, and x takes a new position of pointing to the root node of the right subtree in this case. And then now we compare 18 and 13, and so again 13 is less, and so we move along the left subtree. So, now y becomes pointed to 18 and x becomes pointed to 15, which is the current node. And now we compare 15 and 13, 13 is less than 15, and so 13 is going to become the left child of 15. So, by the time x would be 13 and y would be 15, right. And after that, as you know, there are by this time how we take the decision of putting up 13 in place of I mean as a left child of 15 is that at this point of time, after as we proceed to take the next step, y should take the value of x. So, y has taken the value of 15 and x is having a value of null, because there is no left child for 15, and that is where we stop and put up the value of 13 in place of x. So, that 13 becomes the current node at this point of time. So, we say that after putting up 13, insertion is complete and successful. So, the same thing has been put up in the form of an algorithm. So, we have we follow the procedure. So, this is first two steps are part of initialization. As I said before, current pointer is initialized with the value at root, and the trailing pointer y is initialized with the value of null. And now we check whether the root is not null, only then we can do insertion, and we are going to navigate, and so we are going to assign the value of x to y, and then we compare the key value of z and key value of x. So, if suppose the value at root is I mean value of z is less than the root, then we proceed along the left subtree, otherwise we move along the right subtree. And then y is assigned the value of parent of z. So, that is how we I mean shift the trailing pointers, right. So, for doing that we have this statement, and if y is null, then it means z should be the root of t should be replaced with z, which means the tree is actually empty. Else if key of z is less than key of y, so in that case what we do is that we make a search along the left subtree, and if it is otherwise we make a search along the right subtree. So, here the thing to be noted is that we always as every node in this tree holds this search tree property, we make a decision as to move along the left or right depending upon the search tree condition, whether it turns out to be true or false. So, the average running time for doing this insertion operation is that it is order of h. So, here we have a slide on how to do analysis for insertion in a binary search tree. I hope you remember how to perform analysis. So, we usually take step count into account, and here you could see that there is one loop, and that loop covers up lines from 3 to 7, and all other statements are out of the loop. So, naturally when statements are out of the loop, we give the value of 1. So, that is how we have for initialization and lines 1 and 2, and for all the lines other than 3 to 7, running time is taken as order of 1. So, when it comes to loop, it runs for h times, which where h is the height of the tree, right, or number of nodes in the tree. So, that is why we say that running time for doing insertion operation is order of h. Now, we move to the next operation on a binary search tree, namely deletion operation. So, when we want to remove any node from a binary search tree, then we are supposed to do this. So, for doing deletion, we are having 3 possibilities. One is that we are going to delete a node that does not have any children. So, then the case is very simple. We can just remove the node, that is, we can free up the space allocated for this particular node. So, in our example, we are going to delete 13. As you see, 13 is a node that has no children, and so we can very well free up the space allocated for this particular node 13, and pointer to 12 has to be revised in such a way that its right child is null. So, that is the only thing we have to do if the node has no children. The second case is that we are going to delete a node that has one child. So, now this cannot happen immediately. We need to endorse this child with the parent or attach this child with any other parent. Only then we can proceed with deleting that particular node z. So, before deleting that node z, what we do is that we look at parent of z and we make parent of z to point to z's child. So, that is how we do deletion of a node with one child. Imagine that we are going to delete 16. So, our z is 16. We look at its parent. So, its parent is 15. So, what we do is that instead of parent 15 pointing to 16, what we do is that we make parent 15 to point to its child, which is 20. So, these are the two pointer manipulations which we may have to do for carrying out deletion of a node with one child. So, after doing this deletion operation, this is how your tree should look like. So, followed by 15, we have a link to 20. So, this is how the tree will look like. The third case for doing deletion operation is deletion of a node that has two children. So, here we have to handle this case a little bit carefully. So, the z's successor, we are, if in case we are going to delete a node z that has two children, then we are going to find a minimum node, a node with the least value along the right subtree, because we are going to put it in place of this node. So, this node being root node having left and right subtrees. So, we want a suitable value to be replaced with. So, for replacement sake, it is just like finding successor. So, successor is naturally the node along the right subtree, but it should have a minimal value among the set of elements in the right subtree, and so that will be substituted in place of z. And z's successor, let us call it as y, and there are other things to be noted or taken into consideration here, that y can be either a node with no children or it could be a node with one child. So, here then this should happen in the way as we saw for previous cases, case 1 and 2. So, if in case it is a node with 1 or 0 child, then we can delete that particular y from the tree and replace it in place of z. So, that is how we do. So, imagine that we have this particular example and we want to delete the node 5 from this tree, and as such 5 is a node with two children 3 and 12. So, we cannot straight away delete this node. So, for doing this deletion, I have to find a node along the right subtree with the least value. In our case, the least value is 6. So, I have to delete 6 and put it here, but deleting 6 is also not straightforward, because 6 is a node with again one child. So, what I do is that I follow the rule for case 1. So, when we are having a node with one child, then what we should do is that before deleting we should find its parent and make its parent to point to that particular node. So, in our case 6 parent is 10, and so 10 is made to point to 7. After that, after doing this pointer change, now 6 is free to be deleted and 6 will be replaced in place of 5. That is the change you see here in this tree. 6 has occupied the place of 5, and for 7, 6 is no more the parent, instead its parent is 10. So, this is how we do deletion in situations where a node has both the children. Now, we look up the algorithm for doing deletion on a binary search tree. So, here the algorithm actually takes two things into account. One is the tree and its root. So, first one is the root node of the tree and other one is the element to be deleted. Imagine Z is the node to be deleted. So, we check whether Z has left subtree and right subtree. So, in this case, if left subtree is equal to null and right subtree is equal to null, then it is very simple, which means either this is null or that is null, which means it has either left subtree or right subtree. So, in that case we assume that Z is a node with one child, and what we have to do is that we have to look at Z's parent and make that as parent for the child of Z, right. And otherwise what we say is that if both the conditions are, if this does not hold, that is either both are having both are not null, then in that case what we have to do is we have to go for condition 3 or case 3. We find the tree successor for the node Z, we find its successor. Its successor would naturally appear along the right subtree, and that it should be minimum, and Y is its successor. And other possibility is its left subtree is null, left of Y is null. We are finding a successor, the successor is Y, and its left subtree is null. So, if left subtree is null, then what we have to do is that we make I mean whatever that is left of Y will be X, and if suppose this left of Y is null, then we find make a search along the right subtree. And there is another possibility is that if X itself is not null, in that case what we do is that we make the parent of Y to be parent of X. If suppose parent of Y is null, then we make X to be the root of the tree, and else if left of P of Y, that is parent of Y is equivalent, I mean else if Y is equivalent to left of parent of Y, then what we do is that we make X as the parent of Y's left child, otherwise we make X as parent of Y's right child. So, as such we are taking up 3 conditions into account. We check whether it is a node with one child or 0 child, or a node with 2 children. If it is 2 children, we proceed with finding successor, and while finding successor also we are supposed to check whether it is a node with one child or 2 children or 0 child, right. Accordingly we take paths, and if in case Y is not equivalent to Z, then we put up key of Y as key of Z. So, naturally the time for doing this deletion operation would be of the order of h, where h is the height of this binary search tree. So, I have put up one more example for explaining how deletion actually happens. So, first we have this tree where I want to delete 60. So, 60 is a leaf node, which means there is no children for it, and so I can straight away delete it. If I think of deleting 50, then it is a node with one child. So, for finding, I mean while deleting a node with one child, I should look up its parent and make it parent point to the node, that is what happens. And for deleting 100, the 100 happens to be the root node of this tree, and in our case it is a node with 2 children. So, what I should do is that I should find a successor along the right subtree, and that should too it should be the minimal. So, in our case 120 is 1 and 120 does not have any child. So, I can straight away delete 120 from here and put up 120 in place of 100. So, now in this slide what I have shown is how to add elements to a empty binary search tree. In certain cases, you may be given with set of keys and you are supposed to add those elements onto an empty binary search tree. Imagine that the first element to be added to the tree is 7, then 7 naturally becomes the root of the binary search tree. Then the rest of the elements are added up to the tree following the search tree property. While adding 20, I check whether it is greater than or less than 7. As 20 is greater than 7, I add it as its right child. While adding 5, I compare with the root, it is less than 7, so it is added as the left child. So similarly, I add up the elements 15 greater than 7, so added along the right subtree, 10 also greater and so added along the right subtree, 4 is less than 7 and so it is added up along the left subtree. And so here you could see that there is one more 4, which means it is a duplicate. So normally we don't add duplicates onto a tree, we say that it already exists, and in certain cases we can also permit adding duplicate elements onto a tree. If so, you may have to add up additional rules whether the duplicate element should be added as a left child or as a right child. So without setting up additional rules for adding duplicates, normally we ignore duplicates, saying that the element is already found and so it cannot be inserted. So the rest of the things proceed in the normal fashion. The elements that are greater are added along the right subtree and lesser are added along the left subtree. So now we look at some of the applications of binary search tree. So we have plenty of applications for binary search tree, just because it guarantees ordering of elements, and so it is used for indexing purposes, and it is also used for multi-level indexing too. And for different search algorithms also rely on binary search trees, as it greatly reduces the time for carrying out a search. And if you want the output to be in some sorted fashion, then also you can put up the elements in a binary search tree, and doing an in-order traversal would always guarantee you an ordered listing of elements. So to summarize what we have learnt so far, these are some of the operations that we learnt to be part of binary search tree ADT, like search, predecessor, successor, finding maximum and minimum, and doing insertion and deletion. And all these basic operations usually take up the same time, which is order of H. And these operations are fast if the tree's height is small. If in case your tree is unbalanced, or if in case your height of the tree is large, then its performance would be more or less similar to that of linked list that we learned before. So you should keep in mind that binary search tree is a tree or a binary tree with two properties. One is the binary tree property and the other one is the search tree property, and that that makes this tree special because it makes it suitable for applications like search and sorting, and also I mean it guarantees ordering of elements when we do an in-order traversal. Now I have some few questions that helps to test our understanding of the concepts on binary search trees. The first question is, can a binary search tree store duplicate elements? If yes, how should the duplicates be handled? As I said before, we generally don't encourage duplicate elements to be stored on a binary search tree. But if you feel that it is a must, then you should add up additional rules to tell whether the duplicate should be added as a left child or a right child, and so on. Next is, why is deleting a node with two children in a BST non-trivial? How is it usually handled? So we know that for doing deletion in a binary search tree, we have three cases. One of those is deleting a node with two children. So deleting a node with two children is slightly complicated. We cannot do it straightforward. So when we are to delete a node with two children, we need to find a node with least value along the right subtree, and that node cannot be immediately put up in place of the node to be deleted. We need to check up whether the particular node that is going to replace the deleted node has one child or zero children. If 0 children means it can straight away deleted and added up in the place of the deleted node. Otherwise, we need to follow the condition for a node with one child, deleting a node with one child. So, here we are supposed to find the node that we have identified as minimum along the right subtree and its parent. We have to identify its parent, and then the parent should be made as a parent to its child, and after that process only we can delete that particular node and replace it in place of the node to be deleted. Next question is, what is the difference between in-order traversal on a binary search tree and that of a normal tree? So, the difference is that in case of a binary tree, we have only one condition, that a node can have a maximum of 2 children, but we do not have any search tree property there. So, as such the elements can be anything, and as such when we do in-order traversal on it, it is just going to be a listing of elements, but those elements are not going to be in ordered fashion. Whereas, when we do the same in-order traversal on a binary search tree, there the search tree property holds, and as such as all the elements, all the nodes in the binary tree hold that search tree property, when we do in-order traversal, naturally those elements will be be appearing in a sorted fashion. Next is, can a binary search tree be used to implement a priority queue? Why or why not? And to answer this question, priority queue, there the importance is given for priority of the elements, whereas in case of binary search tree, the importance is for ordering of elements. So, I would say that it is not wise to implement a priority queue using binary search tree. Next is pre-order traversal of a binary search tree always sorted? Why or why not? Pre-order traversal won't get your binary search tree sorted, while an in-order traversal would do. And then, why is binary search tree not ideal for indexing large data sets on disks, and what is used instead? So, whenever we deal with large data sets, normally binary search tree is not the option. In that case, we can go with another class of trees called as B trees, which is exclusively for indexing purposes, and that too for large data sets. And of course, B trees is beyond the scope of the syllabus, and so you just need to know that for large data sets indexing purposes, it is advisable to use B trees instead of binary search trees. Hope you would have understood the concepts of binary search trees better with this lecture, and thank you.